Okay, so let's welcome back to the artificial intelligence session 2, right? By for your season of AI, powered by Microsoft Learn Student Community, Amity University, right? So we'll be talking about the various aspects of data in this session for AI and ML, right? This is the very basic session for data. We won't go into much depth in every topic, but we'll cover every topic so much so that you will be able to go into the depth of those topics on your own with the resources provided, right? So, first of all, what is data cleaning, right? We've talked about previously that data is necessary for training a machine learning model, right? Or an AI model every time data is needed, right? But what if that data is incorrect? Your machine learning model won't notice, right? It just finds patterns in the old data to predict new data. But what if that data had some missing values, some incorrect values, some really different values from the normal scale, right? All of these values have to be either updated or removed, right? So data cleaning is the process of detecting and correcting or removing corrupt and inaccurate records from a dataset. Raw data needs to be processed to ensure its quality and reliability for analysis, right? So there's a data cleaning cycle. We first take the data, we merge data sets if we want two, three, multiple data sets for one model. We rebuild the missing data. We might remove the whole row, right, or the record. For example, if a patient is missing their age, we remove the patient themselves, or we rebuild it, right? We rebuild the patient's data, missing data based on various data statistical models, right? We'll talk about them later. And then we might standardize the data. Again, we'll talk about that later in either in this session or the following sessions, and then normalize the data. We'll talk about that in this session, and then deduplicate. Okay. For example, if say patient X has two rows and both of them contain separate things, generally we may use that for this particular example, but we don't want to use two rows. We just want one row of one patient or one entry or one record of one patient. So we deduplicate the data. Then we verify and enrich the data. Then we export the data back to the model. And then the cycle may continue, may or may not continue, right? This is done to ensure the quality and reliability for actual analysis or usage for training AI models, right? So, first of all, let's talk about handling missing values. If you can notice in this table, or as we would call it, a data set, right? There's data where passenger ID 1 is the, let's talk about it as PID. So PID 1 is one passenger and his or hers data is recorded over here, right? And then we are missing the cabin number over here. And for PID 3, we are missing the cabin number again. For PID 6, we are missing the age and the cabin number. And for PID 5, we are missing the cabin number again. So these missing values, if we train our model, you can think about this yourself, right? It is trying to form patterns based on data. If we train our model on data which has missing values, then our model will get confused and take those missing values into account when they shouldn't have been taken into account. And this will cause it to give fuzzy or wrong predictions and reduce our accuracy of the model or the predicting power of the model. So there are three ways to deal with these missing values. We may remove the complete record. For example, 2 is a full record. Everything has been recorded correctly. So we will leave that and then remove row 1, row 3, row 5, and row 6. We'll be only left with 2 and we'll be left with 4, right? Now, if you can see a very big problem with this, and you must have noticed there are 6 rows or 6 records, and we've removed 4 of them. Now are only left with 2. This reduces our overall data size by so much, right? This has reduced it by a lot, right? 6 has become 2. It's one third of the original size. We do not want this. So for this, we impute the values or replace the missing values with nearby estimates. We can estimate which value should have been there. We may use mean, median, or mode. Mean is the average, right? Median is the middle value in the range of values, and mode is the most used value. These are all statistical mathematical terms, right? We may use any of these three to fill out the missing values. This is the most common form, apart from removal. Removal is done when very basic models are being created by beginners. We recommend you do removal first, then you move on to imputation. And then after that, if you're creating something for the industry, we use predictive models, which will be predicting, which are separate AI algorithms in themselves, which will be used to predict the missing values instead of the output. Then based on the new rows, we'll train the predictive model itself and the output itself as well. And this will result in higher and higher accuracies every time. But imputation is the most common and widely used form of handling missing values. Now, let's talk about removing duplicates. So, as we talked about, we may not want multiple rows of the same person, right? Our model might get trained on one person only. For example, if someone from, say, uh, India, right, and his height is on, we are trying to find the correct height based on countries, right? Now, if someone named, say me only, if Anant, say my height is 6 foot, right? And I'm from India, right? And I train the model three times based on my data only. Then the model will be skewed so that India's data will be skewed more towards 6 feet, even though other people had 5'10, 5'11. This really, really reduces our model accuracy. We do not want this to happen. So in this case, we remove the duplicates. Duplicates in a dataset are redundant and can skew analysis. As we just talked about this, it can skew analysis to 6 feet, right? It will be similar to an echo that distorts the original message. Effective data cleaning involves identification. First of all, you have to identify which rows are duplicates. For example, over here, if we can see, David has 2 rows, right? Martin has 2 rows, and I can't find anyone else, right? So based on these, if we train it on David 2 times and Martin 2 times, so for Latvia it will always start predicting bronze medal, and for Geo it will start predicting silver medals, which is obviously incorrect. There may be multiple entries which may suggest otherwise, but in this case, our model has been skewed or the original message has been distorted. Right? Then we remove or consolidate, ensuring that each record is unique, thus preserving the dataset's accuracy. Okay. Now we've talked about outliers, but let's see it in a more visual form. So imagine this is your more this these are your all the points or the data individual data records plotted in a graph. In this case, a 2D graph, right, from your data set. Now, if you notice something, this is not lying. If we were to make a mathematical function for these, this is not lying within the original parameters. And these kinds of outliers will really reduce our accuracies. This is why we use separate test sets and separate training sets so that we can recognize, okay, this model has been overfitted, or our function goes up to here in a singular line, then suddenly does this and comes back and then does this. We do not want it to do that. We want it to go like this because we are predicting the general outcome. We do not want to predict random outliers, which may be freak incidents, freak accidents, right? If you drive these, you're driving the speed limit, you want the model to predict, okay, the accident didn't occur. But sometimes you were driving the speed limit and the accident did occur, in which case that will be an outlier, and your model might predict for some kind of speed. For example, at 5 kilometers per hour, it may predict that you had a crash, this which is incorrect, right? You do not want that. So outliers are data points that deviate significantly from the rest of the data set, much like a lone skyscraper or a very tall building in a field of houses. you'll be thinking that this is a house society, and then from far away you suddenly see a so tall building, and you'll think that this is a suburb, a building kind of area, right? So you do not want that to happen. You want to focus on the houses themselves. They can provide valuable insights and indicate errors in the data. Handling outliers involves, first of all, you have to detect them, which is a very advanced form of using statistics, because outliers, unlike mean, median, and mode, are very difficult to find, right? And then decision is whether to remove, cap, or transform the outliers, which will depend on what they represent: errors, rare events, or meaningful insights, right? Sometimes it can also be meaningful, but for rare events and errors, right, you might not want them or might want them. You have to decide. Now, data transformation. What is data transformation? So data transformation involves converting data into a format that is suitable for analysis, similar to translating a document into another language. This process includes, first of all, normalization, adjusting data to a common scale without distorting the differences in the ranges of the values, and two, encoding variables or converting data, categorical data, into numerical form for algorithm compatibility. Feature scaling is standardizing data so that different features contribute equally to the analysis. So, normalization, what happens is we adjust the data into a very common scale, because we do not want some part of the data to be in the millions and some part of the data to be in the hundreds. Our model might get skewed, because at the end of the day it is a mathematical function, right? You do not want it to get skewed or the training time to increase by a lot, right? So we normalize it into a singular scale. We'll talk about this in more detail in the next slides. Encoding variables, encode variables of data. For example, if I say it was raining, and it is yes, no, yes, no, yes, no, so we can't really expect our general ML model to understand yes and no. As we've talked about this, it has to be measurable. It has to be a mathematical function. So we'll encode it. Yes will be 0 or 1. We'll take it as 1. And no will be 0. So 1, 0, 1, 0. So we have to use encoding for that. And feature scaling is we standardize the data so that different features or different attributes can contribute equally to the analysis of the data. Right? Now let's talk about normalization in a bit more detail. First, let's read the slide. Normalization scales the data into a standard range, making it easier to compare. Imagine rescaling different currencies to a common value for fair comparison. Normalization methods include minimum maximum scaling or min max scaling, which rescales the data between a defined range, which is typically 0 to 1. Z score normalization centers the data around 0 with a standard deviation of 1, useful for comparing different distributions. So what is going on here? As we've talked about it, we do not want the data values to be very skewed or very, 1 million, 1 billion, or minus 1000 or something like that. We want to normalize it between a scale, which is always close to 0, right? In min max scaling, what do we do? It is just one formula. I'll talk about the Z score formula in a bit. So in min max scaling, the newer x or the newer input variable, right? We always normalize or standardize the input variables. We do not normalize the output variables. We let them remain. We might, but we don't generally, right? So in this case, let's take x as a column, right? It's named capital X. Every value is small x, right? This is the original data set. Now we find x dash corresponding to every small x row. For example, for record 1, value of x was 10. Now we need to find x dash, right? X dash will be the newer value of for the record 1. This new data set will then be used to train the model, resulting in higher accuracy and faster processing, right? So x dash is needed to be calculated for every single row. How do we do this? The formula is x dash is equal to the original value of x for that particular row minus the minimum value of x in the whole column, divided by the maximum value of x in the whole column, minus the minimum value of x in the whole column. This rescales the data, even if it is in the millions or the billions, to 0 to 1 in decimals. It does this always. You can use any made up example. You can just put a singular column, write any kind of value, and if you use this formula for every single element and for every single row, you'll find a new x dash or the new value of x, which will for future references become x then after that, right? You'll forget this. So that new x dash will always range from 0 to 1 if you use this formula. It doesn't matter which number you use. Okay. Then Z score normalization has the formula of raw score, which is again the original value of x minus the mean, which is the average of the column divided by the standard deviation of the column. Now, let's talk about what are the formulas for these, right? I'll just shift my screen share to a separate form for Z score, right? So just a moment, and here you go. So this is the newer formula for Z score, not the newer formula, but the formula expanded for the Z score. So what is mu? Mu is the average, which is again 1 by n into sigma from starting from I is equal to 1 to the capital N, which is the nth element or the last element, or xi, which means you add all the values of x, then divide by the number of values there were. Okay? That is n. That is the average. Standard deviation is the root of the 1 by n into this sigma I is equal to 1 to n, which is again the same function as above, minus xi, which is again the same function, xi minus mu whole square. These are simple formulas. You just use these and you get the desired output, right? So that is all for normalization. Okay, so coming back to the PPT. All right, so let's go on. Now, we then encode variables, right? We've talked about encoding variables. So encoding variables involves converting categorical data into numerical format so that our machine can understand, right? Because it is again a mathematical function, it needs mathematical language. And what is mathematical language? Numerical language. Think of it as translating a language into numbers. One hot encoding creates binary columns for each category, ensuring no ordinal relationship is implied. Label encoding assigns an integer to each category, useful when categories have an inherent order. So let's talk about one hot encoding, right? One hot encoding is basically like, for example, you have classes, for example, you have a set of outputs which is A, B, C. Right? Now let's take four binary bits, which is, first of all, what is a bit? It is either 0 or 1, right? Now these four binary bits will first of all be all 0. Now for A, we'll make the last binary bit 1, right? Now all values which will have an output of A will be concluded to 0001. This is a numeric value. And then for B, we'll take the second binary bit and turn it into 1. Now keep in mind that at one time, only one bit will become 1. So for example, it is not like A has become 1. So for B, we'll have two ones. And then for C, we'll have three ones. And for D, we'll have four ones. No. For A, we'll have the last bit as 1. For B, we'll have the second last bit as 1. And for C, we'll have the third last bit as 1. For D, we'll have the first bit as 1. Right? So in this way, we encode one hot encode variables, and this results in our machine learning model to understand those variables. Otherwise, it would not have been able to understand A, B, C, D. Right? Now, what is feature scaling? Feature scaling ensures that all variables contribute equally to the analysis, preventing dominance by variables in with larger ranges. It's like ensuring each gradient in a recipe is measured correctly to maintain balance, right? Methods include standardization, which again centers data around the mean with a standard deviation of 1, right? Making it useful for algorithms like SVM or support vector machines. You'll be sure to learn these in the future. KNNs, K nearest neighbors, right? Normalization, we've already talked about this, rescaling data to a fixed range, typically 0 to 1, which is often used in algorithms such as neural networks. Or normalization might also be used in normal ML algorithms. Even standardization might also be used. Right? So what is feature scaling out of this? Okay, sorry. So what is feature scaling out of this? So we do not want, for example, I've already talked about this, but let's talk about it a bit more. For example, the value of say attribute A and attribute B, or column A, column B. Column B has, 1 million, 2 million, 3 million as values, and A has values of 1, 2, 3, or 100 square foot, 200 square foot, 300. Now we normalize these or standardize these so that our model is not skewed by one column, and every single column, which is for simplifying terms, an adjective or an attribute of the data, has an equal say in the prediction or the output. Okay, which is why we do feature scaling. Okay, right. So conclusion: pre-processing is the foundation of any data analysis or machine learning project. By carefully cleaning, transforming, and scaling your data, you ensure that your models and analysis are built on solid, reliable ground, much like laying a strong foundation before constructing a building. As we've talked about this, why did we learn all of this? We wanted to know what kind of data can be used to train our actual models. If you want to make a model, the most important part is, first of all, knowing the problem to solve. Second, finding a reliable source of data. Then third, you have to pre-process or clean the data, which we've learned in this part, to use in the model. Because if the model uses incorrect data, what will happen? It will give us an incorrect output. Practice will make a man perfect, but practice of the incorrect will make the man imperfect, right? So thank you very much.